So this is where we were in the last class. Uh, what we derived in the last class was the Williams solution for an infinitely sharp crack which is isolated far away from any boundaries of the body. So all the remote loads are applied at infinity. So for this crack, the stress field very close to the crack tip has always got this form where these are angular functions which are predetermined. There's a 1 by square root r term that makes the crack tip stresses go to infinity as r tends to 0. And then the strength of this singularity is determined by one single parameter called K1, K2 or K3 depending on the mode of the crack, which carries all the information about the remote loading and the geometry of the body to the crack tip. So the strength of the singularity is always 1 by square root r. But the nature of the singularity is always 1 by square root r, but the strength of the singularity is determined by the value of K1, K2, K3, which is like a loading parameter of the crack tip. It does not have units of load. It has units of MPa root meter, but it is like a loading parameter. It is a parameter that we can control by controlling the remote loading, controlling the geometry of the body. So the question now arises as to how do we determine K. There are basically four methods of determining K. K can be determined in some cases from the theory of elasticity. It is something that we are going to do now in some detail. K can be determined by numerical means. For example, through finite element method, we will touch upon that. K can be determined experimentally. We will touch upon that as well. And there are energy methods which we will look at later in detail, which give you sometimes an route to determine K as well. So we will start with techniques that are based on linear elasticity, linear isotropic elasticity. And those of you who have done elasticity course might have solved elasticity problems through series solutions, through Fourier transforms, to Green's function methods. What we are going to do here, we are going to use the method of complex variables and a set of equations that are derived especially for linear elastic isotropic materials based on complex variables, based on the theory of analytic functions. And since many of you already know complex variables, I will give you a brief, I'll recapitulate complex variable theory quickly and then go on to show you how it can be used to solve problems in two-dimensional linear isotropic elasticity under small strain conditions. There are lots of conditions here, but those are exactly the conditions under which this equation has been derived. So we are confined to problems of linear isotropic elasticity under small strains anyway. So let me start by recapitulating the complex variable theory and show you how it can be used to solve problems in elasticity. That's what we will do this week. Next week, we will look at how that theory can be applied to solve problems involving cracks in finite bodies.